Alright, so we're going to see how this goes. So we'll try and do some of these notes online. And then if you guys have any questions, obviously, please feel free to check in with me. But maybe this way you can get some more notes and some more feedback while you're in class. So anyway, what does uniform motion actually mean? A couple different definitions here, so probably good things to go ahead and make a note of if you would like to. Uniform motion, we did talk about uniform circular motion last year, but this is just in general. So uniform motion is straight line motion in which equal displacements occur during any successive equal time intervals. Right? So what does that really mean for us? Well, that means that if we're covering equal displacements and equal time intervals, we're moving at a constant velocity, right? So the big thing that uniform motion means is we're moving with a constant velocity. And I do know that it is velocity because they told me it was equal displacements and not distances. Okay, so basically uniform motion is any motion that has a constant velocity. Now that velocity could also be zero, but in this case it's just in general. Could be anything that's constant. The second definition down here is kind of similar to that. An object's motion is uniform if and only if its position versus time graph is a straight line. So again, the reason I say that's similar is if we think about a position versus time graph, right? So we've got our displacement here versus our time. If it's a straight line, so whether it's horizontal or whether it's a linear equation, something like this, what does the slope tell us in a position versus time graph? Well, the slope tells us, right, the slope is the velocity. And if the slope is a straight line here, then isn't the slope constant, right? So once again, this is really just saying the same thing as our first definition. We once again know that the slope and therefore the velocity would be constant for any straight line. Okay, so uniform motion basically just means an object is moving with a constant velocity. Now keep in mind, if I gave you a second position graph and it was a horizontal line, it would still be uniform motion because in this case the velocity would just happen to be zero. So anyway, a couple definitions to make sure you're comfortable with. Shouldn't be too bad. Going back to last year and how we defined, right, our average velocity. So our average velocity was what we worked with a lot, which was just simply velocity equals change in displacement over change in time. The biggest thing that I want to mention right here is you'll see a lot where in Physics C, anytime they're referring to the average velocity or the average acceleration, they put a little line over that, so they put kind of just that straight line over the top. So again, this indicates that it is the average velocity. The reason they do that is we deal a lot more in this course with instantaneous velocity. So you do need to make sure you're comfortable distinguishing between average versus instantaneous. Okay, so average velocity is the change in displacement over a period of time. Quick follow-up question down here says, can the instantaneous velocity differ from the average velocity if it's uniform motion? Well, if it's uniform motion, again, what does that tell us? That tells us that it's a constant velocity, right? Or if we think about the graph, so if I'm thinking about my position versus time graph again, it tells me it's a straight line. Okay, so let's think about this in terms of the context of the graph. We're asking if the average velocity can be different than the instantaneous velocity. Well, let's go back to starters. What does the instantaneous velocity represent on any type of graph, right? So if instead of a straight line I had a curve or something like this, if I asked you to find the instantaneous velocity at that point, remember that's just the slope of the tangent line, right, at that location. Well, in this case, if we know it's uniform motion and we have a linear equation, then if I asked you to find the average velocity from, say, maybe point A to point B, we would just find the change in x over the change in t. So wouldn't we just find the slope between those 2 points? Well, in this case, if I also asked you for the instantaneous velocity at either of those 2 points or really anywhere else, wouldn't the instantaneous or the tangent line here also be the exact same, right, slope? So if we know that it is uniform motion, we do know that the instantaneous velocity and the average velocity are actually the same measurement. It seems like a simple conclusion maybe, but that is actually a very important one, because every once in a while you can maybe use this piece of information to tell you information about either of these two velocities. Okay, so keep that in mind. That is a good one for us to work with. Let's go ahead and do an example then. So this is example 1 on your example page there. The motion of the car is represented by the following position versus time graph. Find the average velocity and the average speed. Okay, so hopefully part A is pretty easy. Again, we basically just looked at that, right? If I want to find the average velocity, and it doesn't specify for what time, so let's just find it for the entire graph. So let's find the average velocity and average speed for the entire motion here. Well, if I want to find the average velocity, right, I know my average velocity, again, I'm going to use that marking above it, is my change in displacement over my change in time. Right? So in this case, I want to look at my displacement. Now the graph's not real specific, so we'll just kind of estimate these numbers. It looks like we probably start here at about 30, right? So we start at about plus 30. We go up to maybe, I don't know if we want to call that maybe a positive 52, 53, something like that. And then we work our way back down, again, close to 40 here, maybe 39, 0, maybe negative 38, 39, and then down here, it does look like that's maybe just a little bit past the halfway mark, so I'm going to go ahead and call that negative 52. If you wanted to round it at something different, that's fine. I'm just going to estimate it here. Okay, so if I look at my change in displacement for the entire motion, right, because that's what I'm concerned with for the average velocity, my change in displacement. I start at positive 30, I end up at negative 52, right? So if I'm finding my average velocity, it's simply negative 52. It's my final minus my initial, which was positive 30, and then divided by the change in time, which we go from 0 seconds to 50 seconds. So divided by 50. Okay, so in this case, we've got negative 82 divided by 50. Of course, we can use the 10 rule and the 5 rule here, so this is really negative 8.2 divided by 5. And then when I do my 5 rule, magic happens, right? Because I'm dividing by 5. Keep in mind that I will actually double that number, but then move it back the other direction. So 1.64. Negative 1.64. So my average velocity is negative 1.64. Keep in mind we probably do want the units in there. And I think units will be a little bit more of a focus for Physics C, so I would definitely try to keep them in. But negative 1.64 does tell me the direction is negative, right? Part B is the real reason that I wanted to throw this question in here, just to make sure we are stopping and thinking for a second, right? Going back to last year, we defined speed as the total distance divided by time. So you have to be careful. The speed in this situation is not just positive 1.64. It's not just dropping the negative sign. Okay. Instead, what we have to do is we have to think about, well, what's the total distance that I went? Right. So my average speed is going to be the total distance, not displacement, divided by the time. Okay. So it is going to be a little bit different measurement because I go forward, right? I go in the positive direction and then I go backwards in the negative direction. So we want the total distance. Well, positively, we went about positive 22, right? And then we go from positive 52-ish to negative 52, which would be another distance of about 104 meters. So I've gone positive 22 meters from here to here, and then from B to F, I went 104 meters. Again, I don't really care about the fact that it's negative because we're just talking distance, not displacement. So my total distance would be 126 divided by 50. Again, 50 for the entire time. Okay, so obviously then if I calculate that, 12.6 over 5, just so I can do my 5 rule, because why wouldn't I, right? Double that number and then move the decimal point back, so what does that end up being? 25.2, so 2.52, right? That's what I get. You guys can obviously double check me. It is a weekend and I'm not really in math mode. So 2.52. But anyway, that is the measurement that we get for the average speed. So I do want you to notice that on this particular example, the average velocity and the average speed aren't just the same number with a plus or minus sign. They are actually two completely different values. So make sure you are paying attention to that. Okay, this is a good example for a couple reasons. So we'll work this two different ways, and then I'll show you kind of the easy way to do it, and then I'll show you the more generic way that we should probably get used to working these. So Bob leaves his home in Chicago at 9 a.m., travels east at a steady rate, so a constant basically, 60 miles per hour. Susan, who's 400 miles away, leaves at the same time, travels west at a constant 40 miles per hour. Does ask where will they meet for lunch. So actually, because it says where, I'm probably not really worried about the time, although we could work with that if we needed to. Here's the easy way to do it. We know that they're both traveling at a constant velocity, right? They're both traveling at a constant rate. So if I wanted to think about it, well, because it's a constant velocity, right, the only relationship we work for a constant velocity is my displacement over time. So if I do this for each Bob and Susan, so here's Bob, here's Susan, right, I can think about what's their velocity and displacement in time. The key here is, what do we know takes the same for both of these? Well, they don't necessarily cover the same distance, but by the time that they meet, haven't they traveled the same amount of time, right? So t becomes kind of the commonality that allows us to work with this. So here's the easy way to do this. If I solve for each of these displacements, which is going to be a different measurement, right? But if I solve for each of them, so I've got the velocity of Bob, that was a terrible V, let's try that again. I solve for the velocity of Bob, so I'm just going to multiply both sides by t, right? So here's my displacement that Bob has gone. Okay, right, solved for my displacement. If I do the same thing for Susan, I would just take t times the velocity of Susan, which equals to her displacement. What do we know about these two displacements together? Right, so they're both traveling at a constant rate. We can set up these two equations. Collectively, by the time they meet, haven't they traveled the entire 400 miles? Right, so the easy way to work this problem, the easy way to work it, is to just say, well, I know that whatever distance Bob goes plus the distance that Susan goes has to total up to be 400 miles. And notice, because everything is in miles, I'm not worried about any conversions or anything like that. Okay, so in this case, then if I just substitute these values in, right, if I take in Susan's and I plug that in for Susan over there, and I take Bob's and I plug this in for Bob's, and my handwriting again is not very good, but that's alright. Then I've got the velocity that Bob's traveling times the time, plus the velocity that Susan is traveling times the time, and then that has to equal a total of 400 miles. The reason this is helpful is, obviously, if I read through the rest of this question, the only variable that I now have is t. And it is very important, right, that that t was the same for both of them. So I basically just end up then with 60t plus 40t. Keep in mind I'm keeping it miles per hour. Equals 400, so 100t equals 400. So this tells me that it's going to take a time of 4, and right, keep in mind this is hours. So it's going to take 4 hours for them to meet. Now the question does ask, where will they meet for lunch, and not when will they meet for lunch. Okay, so if it was when, we'd say 1 o'clock in the afternoon, but in this case we still would then need to use this with either one of those two equations. Okay, so maybe I come back over here to Bob's and I say that, let's say that Bob was starting at a location of 0, right? So Bob's over here, his initial displacement is 0. We know his velocity was 60 miles per hour, and now we know the time is 40. So then Bob traveled 240 miles, whereas Susan only went 160. Okay, so make sure you do actually answer the question, where will they meet? So 240 miles from Bob's original location in Chicago, or 160 from Susan's in Pittsburgh, excuse me. So anyway, that's our actual answer, right? 200 miles from Chicago is maybe what I'll say, from Chi-Town. There we go. Anyway, hopefully this wasn't too bad, right? That should have been maybe a little bit easier. The second way, though, the way that you can work this as well, is take advantage of a system of equations. So you don't necessarily have to rework this here, but I am going to start to set it up a little bit because it will be very important. So again, if you're working through this, if you're setting it up in terms of a system of equations, right? So if I'm saying the velocity of Bob equals his distance divided by time, and then the velocity of Susan equals her distance divided by the time. So if I look at this right now, I have two unknowns. I don't know the time, assuming I haven't found it yet, and then I have the distances that I don't know. But because time, once again, is a common factor here, you can do any number of things, right? You could solve one of these equations for t and then substitute it back in. The other important thing is, if I know that the total distance is 400 miles, then if Bob travels this distance of xb, what would Susan's be in terms of that, right? Well, if the total distance is 400 miles, then wouldn't Susan's be 400 miles minus whatever Bob has gone, right? So this would be one where I could substitute this in over here. Now I have two equations in the same two variables, xb and t, right? So then if I use a system of equations, I can solve it the rest of the way. I won't make you do that. If you want to try it, it does get a little bit more complicated, but it's still probably worth a try. The reason I mentioned this is, in this course we will see a lot more examples, and we'll see a few in the next part here, but we'll see a lot more examples where you actually have to do some systems of equations in order to solve it. Okay, so I'll go ahead and stop the first part here, and we'll pick up with the next example for part 2 of your first section of notes. Alright.